Hello, welcome. Let's start solving the problems in the past question for CHE 823 mass transfer operations. Now, if we look at the first question there in the past question for 2016/2017 academic session, we have a countercurrent extraction plant is used to extract acetone A from a mixture with water. So we actually have acetone and water by means of methyl isobutane. So what is actually doing the extraction is the methyl isobutyl ketone, also known as MIK, at a temperature of 25 degrees Celsius. The feed consists of 40% acetone. So the feed consists of 40% acetone and 60% water. Pure solvent equal in mass to the feed is used as the extracting liquid. So if we have the feed to be 100, and you know that the feed is consisting of acetone and water, so we're also going to have MIK, which is methyl isobutyl ketone, to also be 100, and it's pure, so that means it's also 100% of MIK. Pure solvent equal in mass to the feed is used as the extracting liquid. How many ideal stages? So the question here is number of ideal stages. How many ideal stages are required to extract 99% of acetone fed? So that is the question. In some cases, you can also be asked, what is the extract composition after removal of solvent? You can also be asked about the extract composition after removal of solvent. So this is what we are going to be solving. So let's get started immediately. So I'm going to delete this so that I could start afresh. So let's start by saying solution. Now, number one thing that we'll do here is to use data in the ternary diagram to prepare a plot of the equilibrium relationship which you are supposed to be given. So you're supposed to be given the equilibrium relationship of YA versus XA. That is the acetone in the solvent and the acetone in the diluent. So you're supposed to be given a ternary diagram. That's where you're going to be looking at and be doing other things. So number two is that you have to check the basics, which is feed of 100 mass per unit hour, which we are already given. The question says pure solvent equal in mass to the feed is used. So because it's pure solvent, we are going to have that pure solvent, which is MIK, methyl isobutyl ketone added will also be equal to 100 mass units per hour. Now, noting these bases, the third thing we'll now do is to calculate the S of F. As in the feed, what is the constituent that is water in the feed? And we're already given that water is 60%. So how do you calculate it? You say 60 over 100 times 100 all over mass of solvent 100 plus mass of mixture 100. If we do this calculation, we'll get 0.3. Now, if we also do in the feed again, what is the acetone in the feed? We already know they told us it's 40, so it's going to be 40 over 100 times 100 all over 100 plus 100 feed plus solvent, which will give us 0.21. Now we are going to do S of F for the MIK. We know that is pure solvent, so it's simply 100 all over 100 plus 100, which will give us 0.5. So these are the missing fractions. So we just found the mixing fractions. So at the point of mixing, that is what we'll have. So we are going to take note of this so that we can then move forward. So I'm going to delete this so that I can continue. So now we do the fourth thing. Now we say that SF of water, which we have already found, SF of acetone, which we have already found, and SF of MIK. This combination of all these fall on M. Very, very important in the diagram. If you draw the diagram, you find this out, which is within the two phase region. It's very, very important to notice. And after noting this, number 5, we are going to say let N be equal to mass flow rate of H2O in extract. But before this, we are supposed to have this diagram, which is actually the number 5. We're gonna have that the liquid goes in from here with this flow rate LA and this mass fraction coming out here as LB with this flow rate and this mass fraction, whereas the gas goes in from here with this flow rate VB and mass fraction, and comes out here with the flow rate VA and mass fraction. So this should actually be the 5th thing we should do before we now say the system, which is let N be the mass flow rate of H2O in the extract. This N representing the mass flow rate of the diluent. The diluent is anything that contains the solute. Now, having said that, we can now say also let M be the mass flow rate of the solvent. Whenever you consider the diluent, you consider the solvent. The solvent is methyl isobutyl ketone, MIK, in the raffinate. That's the 6th thing you do. Then the 7th thing is, now you say that for 99% recovery, which is what you are supposed to find, for 99% recovery of A, the extract will have what? The extract has 0.99, which is 99% times 40, which is equal to 39.6 acetone, and the raffinate has 1. Since this one has 99%, is 99 over 100, so this one will be 1. 100 minus 99 is 1, so this one will be 1 over 100 into brackets 40 over 100 times 100, which will give us 0.4A. So that's what is in the raffinate, 0.4A. So that is where we are now. So I'm gonna delete this so that I can continue. Now let's get to the number 8 thing that we're supposed to do. Now we say that the total flows are, that is taking a material balance. We have at the top LEA is equal to F, which is equal to 100, which is equal to 40A plus 60 H2O. Remember this diagram that we drew, where we have the liquid going in here and coming out here, whereas the gas is going in here and coming out here. So this LA is the liquid flow, which is the feed flowing in, and it's actually 100, which is 40A plus 60 H2O. Whereas VA, which is this vapor flow out, is equal to 39.6A plus N H2O. You know, when we mentioned N, plus 100 minus MIK is the material balance. If you break this thing down, this very thing down, you are going to have 139.6 plus N minus M. That is at the top. Then at the bottom, VB is equal to 100 MIK. We already know that. Then LB is equal to 0.4 A plus 60 minus N H2O plus MIK. If you solve this out, you have 60.4 plus M minus N. So that is the material balance. Very, very important. You need to get down this material balance. This is for the top and this is for the bottom. So having gotten the material balance, we'll now move to the ninth thing to do, and that is saying that since n and m are small and tend to cancel, they are very small, so they tend to cancel in summation for VA and LA, the total extract flow VA is about 140. Instead of having 139.6, we approximated it to 140, so that you can simply say that YA is approximately 39.6 over 140, which is actually 0.283, and XA is 0.4 over 60, instead of saying 60.4, which is approximately 0.0067. So the 10th thing we have to do is to say that these estimates are, so we made these estimates because we don't have the actual values of m and n, but these estimates are adjusted after calculating values of n and m. So immediately after calculating it, we adjust the estimate. The 11th thing that we should do is that we should know that from the figure that I drew, from the ternary diagram, YA is equal to 0.283, where YH2O is equal to 0.049. 0.049. So take note of that. Very, very important. So with that said, we can now get to the 11th thing, which is using mass ratio of H2O. We can then say that N over 39.6 plus 100 minus M plus N minus N is equal to 0.049 all over 1 minus 0.049. So if you make N the subject, you have 0.049 all over 1 minus 0.049 times 39.6 plus 100 minus M. So if M is very small, as we assume, that means that N is approximately equal to 0.049 all over 0.951 times 139.6, which is equal to 7.2. So that is the value of our N, assuming that M is very small and approaching no value. The 12th thing that we do now is that from the ternary diagram, for XA equal to 0.007, x mlk is equal to 0.02. So using that, we can now say that, using mass ratio as well, we can now say that m over 60.4 plus m minus n minus m is equal to 0.02 all over 1 minus 0.02. So this is going to make m to be equal to 0.002 all over 1 minus 0.002 into bracket 60.4 minus n. But we already know that n is equal to 7.2 from this very calculation, so that m now is equal to 0.02. There's no double zero, just 1 0 here. 0.02 all over 0.98 times 53.2, which will give us 1.1. So using m as 1.1, if you go and do this calculation again, putting 1.1 here, we'll find, like I told you, you have to adjust whenever you get the revised. We'll find the revised n to be equal to 7.1. That is what we will be using in further calculations. So I'm going to delete this so that I can continue. So having done that, we are going to look at the 13th thing to do, which is taking down the material balance. VA is equal to 139.6 plus 7.1 minus 1.1 equal to 145.6. So that YA for acetone is equal to 39.6 over 145.6, which is equal to 0.272. Then LB is equal to 60.4 plus 1.1 minus 7.1, which is equal to 54.4. And XAB is equal to 0.4 all over 54.4, which is equal to 0.0074. So this is the material equation that we had before, but we now have the value of m and n, so we substituted to get all these. Then we'll move to number 14 step, which is taking out the values to establish our operating line. So we have our SA and YA for B, which is actually at 0.0074 and 0. This will be the bottom of the operating line. Then we also have XA and YA of A, which is 0.04 and 0.272, which is at the top. So if you plot this as the bottom and top, you've established the operating line. Very, very important. So I'm going to take this out and continue. So now move down to this 16th step. For an intermediate point, you need an intermediate point to really establish the shape of our operating line. For an intermediate point on operating line, just pick ya to be equals to 0.12. Just pick a random number at the middle and calculate V and L. From the ternary diagram, the Y for H2O at this YA of 0.12 will be 0.03, and the Y of MIK will be 0.85. So this will help you plot the intermediate line. Then the 16th step that we should take is that MIK percentage, we know 54.4 is equal to 1.1, which is actually the MLK percentage in the raffinate, which is approximately 2.02%. Now, the extract contains 100% MIK, that is the same in mass as the solvent feed, same in mass as the feed actually. So we have 100 approximately equal to what the solvent is, so that V is equal to 100 all over 0.85, which is 117.6. So the 17th step that we take is that we say that by overall balance from the solvent inlet, solvent inlet, you know that the solvent comes from the bottom to the intermediate point. We are going to have that VB plus L, which is equal to LB plus V, where L is approximately equal to 54.4 plus 117.6 minus 100 equal to 72.0. Then the 18th step we take is that we say that a balance of A over the section gives XA. So I want to find XA. So we can say that LO XA plus VB YB is equal to LB XB plus V YA. So this will make LOXA to be approximately equal to 0.4 plus 11.76 into bracket 0.12 minus 0, making our XA to be approximately equal to 14.5 all over 72, which is equal to 0.201. So with this, we can actually say that XAYA is now equal to 0.201 and 0.12. This is accurate enough to plot the intermediate point, so you can use this to actually plot the intermediate point. So we can use that to plot the intermediate point. So with that, we just go into graph plotting to determine the number of stages. So with that done, we already know that we have equilibrium data, which is obtained from ternary diagram, and this equilibrium data says that XA and YA, you have the values of XA and YA. When XA was 0.025, YA 0.048, at XA 0.05, YA 0.10, at XA 0.10, YA 0.18, at XA 0.15, YA 0.25, at XA 0.20, YA 0.32, at XA 0.25, YA 0.37, at XA 0.35, 0.30 actually, YA 0.40, at XA 0.35, YA 0.44, at XA 0.40, YA 0.46, at XA 0.425, YA 0.47, and finally at XA 0.49, YA 0.49. So this is the concentration of the acetone in the raffinate. Take note, where this one is the concentration of the acetone in the extract. So the above is given by the ternary diagram. So we'll now use it to plot the equilibrium line. We use the data from the ternary diagram to plot the equilibrium line. You understand? Whereas we use the calculation data to plot the operating line. So if we have this as our graph, then we'll have from here 0.1, 0.2, 0.3, 0.4, 0.5. We also have here 0.1, 0.2, 0.3, 0.4, 0.5. So using this, we can plot from the calculation we had before, can easily plot the operating line as this. So here this is the operating line. Then we can now plot the equilibrium line. Plot the equilibrium line like this. So where this is the equilibrium line or curve, so the place where it ended here, call it the plate point. Now we can now draw the number of stages. So we can easily find out that the number of stages 1, 2, 3 point something. So this gives the number of stages to be equal to 3.4 stages, and that is the answer to the problem. Please, if you have further questions, you can drop it on the comment section. Thank you, and God bless you. Hit the subscribe button to subscribe. Thank you, and God bless you.